BMW didn't have a turbo rotary engine in mind when they designed the i8, so today we're going to design a 3D printed exhaust that will handle the spiciness. The last major component that I need to design for the turbo rotary swap going in my i8 is an exhaust that's on par with the rest of the build. It's a bit of a tragedy that most of the stuff is going to be hidden away out of sight, and there's really no visual indication that something other than stock is going on, and I'm not the type to rivet on some over fenders, so designing the exhaust is going to give us the opportunity to not only let the rotary breathe, but give some sort of visual indication that something other than an uninspired hybrid is afoot. The factory exhaust exits out the bottom of the bumper facing downward, which is less than ideal because rotaries are known for being off-throttle flamethrowers, and with heat and fire wanting to rise, the only place for it to go is to cook the bumper. The path forward is going to be a McLaren-esque style exhaust that's going to exit the rear bumper near the license plate. As veterans of this channel might expect, much like the rest of the induction system, this is going to rely heavily on 3D printed metal, and the first step is going to be to 3D scan the area in which we're going to work. While I did do a quick and dirty space claim of this area in the past, it's not going to be accurate enough to invest in a hefty chunk of laser sintered metal dust. For the past year or so, I've been using the Einscan Rigil all-in-one scanner for most of my projects. Out of the box, I expected this to be a bit of a toy, but it's really proven itself to be a fast, reliable, and accurate scanner. Shining 3D recently released the Rigil scanner, which is a similar concept, but adds the functionality of both parallel and cross laser lines. With how much I liked the Vega, I reached out to them to see if they'd be willing to send me one to try out, and they graciously loaned me one for a couple months. One important differentiation here is that the Vega is part of their Einstar line, whereas the Rigil is part of their Einscan line, which is focused on the professional grade tool. This is one of the things that I like about Shining 3D, is that they were already established in industrial and dental scanners, and their entry into the hobbyist market was a trickle-down effect rather than starting at the bottom and trying to work their way up. As such, the Rigil is priced at about $5,000, which is significantly more than the Vega, which has a $2,000 price point. So let's take a look at what the differences in these are. The biggest distinction is the addition of the laser mode, and as I said, has the option of 7 parallel laser lines or 19 by 19 cross laser lines, and you can switch between these two while you're actively scanning based on the features that you're trying to capture. The minimum point cloud distance for both of these scanners is 0.05 millimeters, but the laser is going to offer much greater detail around edges and around holes to make reverse engineering things significantly faster. While there are a number of other laser scanners on the market, one of the most interesting things for me on this one is its ability to use the laser mode without markers. I have voiced my distaste for markers in the past on this channel, and this is a huge time saver in not having to apply and remove markers. Furthermore, I scan automotive parts, many of which are used, and getting adhesive stickers to stick to used components can be quite difficult, so it saves you the cleanup time there as well. Another key improvement for professional use over the Vega is the addition of swappable batteries. While the battery life of the Vega has proven adequate for my needs, if you're going to be scanning for a long period of time, you're either going to have to plug it into a power bank or stop and recharge it mid-scan. Whereas with the Rigil, you can just swap the batteries out and then continue along with your workflow. The on-screen user interface is very similar to that of the Vega, but it offers an improved file system similar to that of the X-Star software, where you can have multiple scans and combine them into a single project, which allows for easy export onto the PC. Just like the Vega, this can operate in a full standalone mode where you can capture the scan, do the point cloud processing and the meshing on the device, or connect it to a PC over Wi-Fi or cable, and then use it in conjunction with the X-Star software. The standalone mode can capture at 50 frames per second, but if you are connected to a laptop via that Wi-Fi or cable, that will increase to 90 frames per second. Speaking of scanning PC software, I don't think anybody really offers a world-class user experience, but I really like the X-Star software in terms of its flexibility, as well as its post-processing and its 3-2-1 alignment tool. So that's enough about the device itself. Let's get down to it, get the car torn apart, and begin our scan so that we can design an exhaust. First order of business is to get the car up on our race ramps wheel cribs, and then we spend what seems like the next hour taking fasteners off the bottom of this car because BMW was seemingly very worried about this thing falling apart. Since we got this thing apart, we'll see what it sounds like with an open downpipe. And we should realize some easy weight savings with the new exhaust. As I mentioned, the Rigil is capable of laser scanning without the use of markers, and my intent was to do this entire project using that functionality. As it turns out, I'm an idiot and didn't read the manual, and I had the car all set up with scan spray, only to realize that to use that mode that you have to be connected to the laptop via Wi-Fi or cable, and this turned out to be a really good opportunity to flex the Structure Light IR mode and compare it to the Vega for its speed and ease of use. Before starting the scan, I hit all the black surfaces with ASIB scan spray, and I rarely scan anything without using this stuff. It's well worth the cost over some DIY alternatives that can be somewhat difficult to clean. We're going to do a continuous capture of the scan. This way you can see the working distance from the vehicle as well as the motions needed to fully capture all the surfaces. The Rigil has been by far the best tracking 3D scanner that I've personally used to date, even when working your way around the edge of the bumper, which is a transition that can often be somewhat difficult. Here's the mesh result of a sub 5-minute scan in the X-Star software. I generally keep all the smoothing to 0, which is why you'll see some roughness on the surfaces. X-Star offers a good variety of options for post-processing the mesh, and the feature that I use the most is for aligning the scan to a coordinate system. As you can see, the orientation here is less than ideal. The 3-2-1 alignment system lets you select a plane, a line, and a center point, and that'll allow you to quickly square up the scan and then easily position that once you import it into your CAD software. The first part I designed was the bumper insert that'll be 3D printed in aluminum. Many newer cars have the aesthetic features of the exhaust tip built into the bumper with a less ornate exhaust pipe centered within, and that's the approach that we're going to take here. With our fresh scan imported as well as a previously done mesh of the plastic panel we'll be modifying, the first step was to use the forms tool to create a surface that will be the base of our design and ensure that it fits tightly to the curvature of the bumper. There's a center line created so that we can have Fusion mirror the part automatically and only focus changes onto one side. Since we're dealing with a flexible plastic panel, you don't need to go too crazy making it sit perfectly to the scan. Poking through the mesh here or there is perfectly fine, and you can see that the max deviation here is only 0.8 millimeters. Working in forms are two primary views, being the box display and the smooth display. You want to do most of your work in the box display as it will highlight any irregularities that will impact the final shape. You can see that dragging things around in smooth display doesn't appear to make much difference, but the control points are all over the place if you switch back to box display. Next, I started roughing out the exhaust tip that will blend with the shape of the bumper. For this, I used a mesh section sketch for the upper curvature and then closed off the sketch with some gentle arcs. To get it to match the curvature of the bumper, I did another mesh section sketch and then offset that so the tips will protrude beyond the bumper and then use that shape as a cutting tool. The rest of the tip was just some lofts and fillets to bring us to the final shape, and again, we're going to mirror that for the other side. To build out the rest, I then roughed in some material to connect the tips side to side, as well as have a mounting location for the license plate. I sketched up some hexagons to give it a little more visual detail, and the emboss tool was giving me some problems here, so I decided to just extrude the matrix of hexagons, and then used an offset body from our original baseline surface curvature to keep the thickness consistent throughout. This print is too large to do in one piece, so I split it with some dovetail joints for alignment, and also added a small clearance for the reverse camera. Apparently, if you don't have all the components installed when you scan a part, you can't design around them. With that component design, let's take a look at the exhaust itself, which really isn't too complex. I did spend a fair bit of time positioning the flex bellows so that the system could be compatible with both the OEM B38 downpipe as well as the 13B swap. I designed it to mostly use standard commonly available mandrel bend radii, as I hadn't really decided whether I was going to have the full exhaust printed. The mufflers are 2¼ inch inlet vibrant ultra quiet resonators. I've used these for years and they seem to sound good on pretty much everything. Splitting it into two smaller diameter pipes rather than a larger single should help prevent some of the drone on the highway as well. Since I did ultimately decide to 3D print the tubing for the exhaust, I was able to incorporate the exhaust hanger tabs directly into the part, And for the tailpipes, transition from round to oval to give us more clearance to pass over the bumper support, which will still need to be trimmed a bit, as you can see here. The main portion of the exhaust is split into two pieces, and while this did fit into the build volume of the manufacturer's 3D printer, there would have been supports that would be difficult or impossible to remove. Before we put the finishing touches on the design, we need to make some of the bumper support go away and then scan the car with some fresh OEM hangers bolted in place because the originals had seen some better days. With the hangers bolted into place, we'll utilize the markerless laser scanning option on the Rigil. This requires it to be used with the laptop over Wi-Fi for some additional compute power. It is worth noting that this is a little bit slower due to the reduced frame capture rate, but it was well worth the convenience of not having to apply and remove markers. This is the result of our laser scan, and it's worth noting that my approach to 3D scanning is to get the minimum viable result for the intended use case. I didn't need a thorough capture of all the surfaces, but only an accurate reference to the exhaust hanger through holes and the cutouts in the bumper support. Since this is the first time you're seeing the Rigil on this channel, here's a more complete example of what you'd expect from the laser mode with a BMW F-Series shifter. This was done by merging 3 scans and used the markers that live permanently on my benchtop. You can see it generates nice sharp details on the edges and even captures the texture and stitching on the leather boot section. With our laser scan, we'll jump back over to the CAD just to take a look at the exhaust hanger situation. In the rear, we've got a flat piece that is going to be laser cut by SendCutSend and have some M6 hardware already installed. And then we're just going to play a game of connect the dots for the remaining 2 pieces and have those printed in 316 stainless as well. Finally, we can look at the cutouts that we made in the bumper and ensure that our tailpipes can pass through without touching. Those of you who have been following the channel for a while should be no stranger to the services of CraftCloud 3D, and I've used their services to 3D print my turbo manifold, my intake manifold, the charge pipe, the airbox, the inlet pipe, and a multitude of other smaller parts throughout this build. For those of you new to the platform, they are a web-based brokerage that allows you to upload a 3D model and have instant pricing and access to dozens of additive manufacturers across the globe and allow you to select the ideal material, price, and lead time for your project. They have an extensive list of materials to choose from, and we're going to use 316 stainless steel and aluminum for this project. Both of these materials generate parts through the process of direct metal laser sintering. There is no plastic binder involved. With our files uploaded and the material selected, you can see the total price for the project, and we're not going to select any additional surface finishing. Once added to the cart, you can see all the individual prices for the components. Now, these parts are by no means cheap and probably
not economically viable
for every situation, but depending on the platform that you're working on and the availability for quality off-the-shelf parts, this might actually be a relatively budget option. So if you're working on a rear or mid-engine car with an extremely tight engine bay, have a bunch of bends that need to happen in a small amount of space, plus the incorporation of an X-pipe or Z-pipe or something like that, then this is really a viable solution for that type of application. Realistically, the most logical choice for my build would have been to just print the merge collector and the tailpipes where it transitions from round to oval, but I am so far down the path of excessive 3D metal printing that we're just going to go all the way here. Due to the size of the stainless parts, we only had a single vendor and option to choose from. However, for the aluminum side of things, we have far more choices in terms of pricing, manufacturer location, and lead time. All that's left to do now is check out, and if you go to the description, you'll find a discount code for 10% off your first order. While we wait for our 3D printed metal parts, the bumper panel needs to be modified for the exhaust to pass through. I used a series of drill fixtures printed on the Bamboo Lab H2D to accurately locate the holes and cutouts before dropping the panel off for paint.
A few moments later.
Out of the box, these things look pretty good. The only kind of anomaly is you got a little overzealous with the grinder there, probably removing some supports, but that's going to be behind the license plate and it doesn't matter. We've tapped the holes for the license plate. We've got the holes tapped for retention of the bumper as well. I sized these at M6, which is probably a little bit large. Probably could have gotten away with an M5 or an M4, but these will do just fine. These are now going to go off to get ceramic coated, which is going to offer a nice high temperature finish that will not get baked off by any flames coming out of the exhaust. And it will also help to provide a thermal barrier, but this has quite a bit of mass and it's not going to get hot enough to transfer any significant heat to the plastic bumper.
A few moments later.
After waiting a little bit longer than usual with the holiday season upon us, we've got the remainder of our 3D printed parts that we're going to need to finish off our exhaust system, merge collector, the downpipe section, which is going to be for the 13B, the front half of the main exhaust, the two tailpipes, and then a downpipe section that will mate to the factory catalytic converter outlet that will allow us to utilize this exhaust in the interim while we wrap up some CAN bus data logging and other things required before we actually perform the swap. This is stainless steel, so we're going to back purge this with some 3D printed purge plugs. These are just PLA, and due to the location, they're not going to be that close to the weld joint, so that'll be perfectly fine for our intended purpose. These are just a taper fit, and they will contain the argon well enough to shield the backside of our weld and keep everything from getting contaminated. Then of course we have our stainless 3D printed exhaust hanger pieces, as well as our SendCutSend piece and some fresh OEM rubber hangers from our friends at SCP Euro. For normal fabrication, you're going to have to tack things up either on the vehicle, or if you pre-design something in CAD, have to carefully cut, index, and mark all of your mandrel bends in order to tack them together in a fixture before you put it up onto the vehicle. Now, one of the benefits of 3D printing is that you can actually build the fixturing features into the part itself rather than having to have yet another part that's going to be either one-time use for a custom job or take up space in your shop for a long-term period of time. And in the case of the two-piece main portion of the exhaust, it was split in such a way that we have a recess and a lip that's going to positively locate the part, as well as 2 notches for the receiving part. So that firmly locates into place. It can't rock. And because the notches are different on both sides, it can only go in one way. So now we can weld this together and it will be perfectly aligned as it was in the CAD. I built a couple other design features into this as well to help self-locate everything, such as these steps wherever there's a slip fit. Normally, if you're tacking up something on a car, the somewhat sloppy fit that you'll find in a muffler flex section is kind of more of a feature than a bug. But if you've taken the time to precision 3D scan something and then design it in CAD, that extra amount of play is not going to be of any benefit when you go to put it up on the car. You'll also notice on the tailpipe section for the mounting bracket, there are 2 holes. This is not for any sort of strength or load purpose. This is really just to index the part to make sure that the rotational position is correct when we go to weld the mufflers on. We simply take our SendCutSend bracket with PEM hardware, line these up, insert the fasteners, and then these should be perfectly centered within the outlets of our bumper trim. Additive manufacturing can only take us so far in the process, and we do need to finish this exhaust off with some traditional fabrication components. And I have been sourcing my fabrication components for, as crazy as this feels to say, the last 20 years from a company down in Delaware called Motorsports. They are a fully stocked fabrication warehouse that not only do their own mandrel bends and offer multiple bend radii for nearly every size of tubing, but also offer a full selection of flanges, clamps, flex sections, and every other component that you would need to finish off your project. They also carry the rest of the performance parts needed to round out a custom fabricated turbo system, such as Bell intercooler cores, who have a massive selection of sizes, just as the one that I have welded into my otherwise 3D printed intake manifold. They're conveniently 1 day with ground shipping for me here in Connecticut, 2 days for the entire East Coast, and less than a week for most of the country. In today's world, it's often all too easy to default to Amazon or eBay for your purchases, but whether you're a dude in a garage looking to buy all your fabrication components from a trusted source, or a shop looking for a reliable wholesale fabrication parts partner, definitely give a look to the guys over at Motorsports for your next project. The components that we source through Motorsports for this project are the Vibrant Ultra Quiet resonators. They do carry the full line of Vibrant products. And then we used their own private label V-band assemblies and these flex sections. These particular flex sections have an interlocking liner. I've used a whole lot of flex sections over the years, and I found these to be the most reliable, particularly on a turbo application. With the interlocking liner, they are a little bit stiffer, so they're not as floppy as perhaps the factory flex section. But if you require that much flex, then you probably have other issues in the system that you should probably address. Now, these particular flex sections are very similar to the Vibrant TurboFlex series. However, the TurboFlex series in a 3" by 6" length typically retails for about 75 to 85 bucks. And the Verocious private label ones are $55 at present on their website. So just a good prime example of why I use them. You get a good quality part at a reasonable price, and if you do this professionally, offers you a little bit more flexibility on the margin front. With the main section tacked up, we can get the mufflers and tailpipes into place and then see how all this is fitting up. So these are positively located, they can't rotate. Now we can drop our mufflers on. Here we are all tacked up and the exhaust hangers are in place so we can test fit this on the car before we send it home. I did forget to mention earlier that the wall thickness on this is 50 thousandths of an inch or 1.27 millimeters. We've got the V-band flange printed into place on the exhaust side. Along with a locating step. The reason for going with the 50 thousandths thickness is a little bit thinner than 16 gauge, a little bit thicker than 18 gauge, so it's a nice balance between strength and weight. And with 3D printing, you don't have any inconsistencies on the bend. So on a mandrel bend, the outside of the radius is going to be quite a bit thinner as the material stretches to make the bend, and then likewise quite a bit thicker on the inside. But now we have a nice consistent wall thickness throughout the entire part. And of course, we'll need to tack up our downpipe side. On the 13B downpipe, we will need to tap the O2 sensor bung, but we'll do that after we get the exhaust up on the car because we will not need this for at least another month or two. Taking a look at the full setup installed in the car, you see that the aluminum portion of the tip extends out past the bumper, and then the rest of the car kind of curves back in, so any of the flames that might come out of here are going to be away from the upper portion here. So hopefully we'll prevent from cooking anything, but this is all kind of an experiment, and we'll see where we end up. Now, there are probably a number of Rotary owners shouting at the screen saying that this will ultimately cook the bumper, and the mere presence of flames exiting the exhaust don't necessarily tell the whole story, and I've had a bit of a theory on that I've been able to visualize through the use of Airshaper, which is an extremely easy to use CFD analysis tool. This online software allows you to import a solid model or mesh body of a vehicle, position it in the desired airstream, set the speed, and click go. About 20 minutes later, you'll get an analysis of the aerodynamic performance of that body. The result of a rotary-powered car infamous for a crispy bumper trim shows some fascinating results. The profile of the car and the air exiting the undercarriage actually causes the airflow to splash back toward the rear of the car. Not a problem on most vehicles, but when there's an ignited combination of fuel and premix, this is not ideal. If we look at the same scenario for the i8, the air detaches from the car without the same level of drama and should result in a greatly reduced risk of getting a little too spicy. Not only does Airshaper offer external aerodynamic analysis, but also internal flow geometry as well, and we'll look much deeper into that in a future video. So that's where we ended up, and I might be a bit biased, but I think that's how the car should have come from the factory, And thanks to the Einscan Rigil, we were able to capture the area in which we're going to design a part with the confidence that we could invest a couple $1,000s in 3D printed metal parts and know that they would fit after we received them. I've thoroughly enjoyed making all of the 3D metal printed parts, and sadly this was the last major component that will get printed out of metal, at least for the time being. And that means we're getting very close to swapping the car, and it is going to happen over this winter. That means we should have a more steady stream of content over the next couple months, which will ultimately culminate into doing Brappy burnouts. I think that's going to wrap this one up. As usual, if you made it this far, thanks for watching, and we'll see you next time.